All right, so let's go over this problem. So here we're gonna need to use an ice table. A clear indication of that is that there's a KB value. Okay, so let's start with the information that we have. Let's derive some numbers and then we'll get started. Okay. So it tells you that a solution is made by adding NaClO to enough water to make 2 liters of a solution that has a pH of 10.5. So we already got 3 numbers, so it's kind of a good place to stop and just think about what's going on. So let me draw one of my beautiful pictures again. So we got your container, and I'm put some detail. I'm gonna make it blue for the water. Wow, amazing. Okay, so we're gonna add NaClO, and the volume is going to be 2 liters. And when we add the NaClO, the pH is going to be 10.5. Okay, everybody good with understanding that? Okay. Please no Spanish. I failed Spanish, guys.
Oh,
okay,
sorry.
use and then using the information. I did not survive Spanish. Using the info from the equation below, calculate the moles of NaClO that was added. Okay, so first thing we need to identify is that NaClO is an ionic compound, right? And as an ionic compound, and because the cation is Na, we know that anything that has Na as a cation is always soluble, right? It will always ionize. So this is going to ionize into Na plus and ClO minus. And this value tells us to the extent of which. So it's not 100% ionization. Instead, it's just going to be this amount, okay? That's why we need an ice table. So far, so good?
Yeah.
Okay. So because NaClO breaks down into Na plus and ClO minus, we can basically figure out that NaClO and ClO minus have a 1-to-1 mole ratio, right? For every single mole of NaClO that's added, 1 mole of ClO minus is going to come out of that. Make sense?
Yeah.
Yes? Okay. Okay, so what we're going to do is we're going to have to set up an ice table. So let's set up our ice table, okay? So I'll give you guys a minute to set one up. Obviously, I need to as well. So set up your ice table, and then we're going to start filling it in. Yes. Yeah, so we can do that. Yeah, so if you didn't draw that section, that's totally fine. Yeah. Good point. So yeah, pure liquid we don't need to include. Okay, let's keep going. So this one is a little bit different from the problems that we've been doing, because if you notice, we're trying to find the moles of NaClO added to the water, right? So if we take a look at this value that we're trying to find right here, does this have to do with the initial, the change, or the equilibrium value? Initial. This is the initial, because wait, hold on. I can't even spell initial. Guess I failed English too. Okay, so this has to do with the initial value because you need to add NaClO and then it dissociates and then comes to equilibrium. Does that make sense?
Yeah.
So because we're looking for how much is added, we add it at the start. You need to add the chemical before it dissociates, right? I mean, the time might not be that long, but it still precedes the dissociation. So in this problem, what we are looking for is something that has to do with the initial phase. Now we're looking for the initial moles of NaClO, which means out of these 3 compounds, which one of these initial boxes are we looking for? Yeah, top left, ClO. This is what we are looking for. We'll put a question mark. All right, make sense so far?
Yeah.
Okay, let's start putting in the values. Now, at the beginning, we put in a certain... Oh, goodness. We'll wait. Okay, guys, so I forgot my train of thought, but we don't know how much we start with, but we can figure out how much we have in the beginning for these 2. What are the values for these 2? 0, yeah, we don't start with anything because they haven't dissociated yet. Okay, all right, now let's look at the change. Yeah.
So we had a question. What would happen if hypothetically the fire alarm went off during the AP exam?
That's a good question. I don't know.
But,
Like, what if it was actual?
Yeah, what actual fire alarm?
I'm pretty sure you'll have a retest.
So we have to like.
And it'd be a new test?
It'd be a new test.
Probably, yeah.
Oh.
They have backups.
We can't like stop in the middle of it.
I
just,
don't
like,
think so. No.
check our answers.
No. That'd be nice, right?
It would be.
Someone else.
So, okay, so the change here, are we gonna gain or lose CLO minus? Yeah, we're gonna lose, right? Because it needs to dissociate. That means we're gonna gain these guys. And so what's gonna happen is you're gonna end up with X and X for this, and then our question mark minus X, okay? So this looks like a very solvable equation, right? Okay, now before we do anything, we do have one more piece of information that we did not use yet. What did we not use yet? pH. Well, pH and volume, but let's look at pH because that's the one that's more important. Now, we know that the pH here is equal to 10.5. We know that pH is equal to the negative log of H plus, right? Okay, now if you guys remember, we have another equation that we can use. We know that POH is the negative log of OH minus, right? And this is going to be at equilibrium. So if you use this equation or either of the equations right here, you can basically figure out the concentration of OH minus at equilibrium. Does that make sense?
Yeah.
Yeah. So what I want you guys to do is take about maybe 2 minutes. You can work with the person next to you. I want you guys to use the information that you have right now to figure out the concentration of OH minus at equilibrium, which in turn will tell you a lot more information going forward, okay? Take about 2 minutes to do that. See how much of the table you can fill out, and then we'll go over how to finish the rest of the problem. Alrighty, guys. So you should have gotten 3.2 times 10 to the negative 4 molarity. Everybody got that? Okay. So since this is a number that we get from either pH or POH, doesn't matter how you do it. So we can start replacing some numbers in our ICE table. Okay. So the value that we have for hydroxide concentration is 3.4 times 10 to the negative 4. Obviously, here, same thing, 3.2 times 10 to the negative 4. Okay, we know we can start changing all this stuff too. That means that our change here was a decrease of 3.2 times 10 to the negative 4. And here it was a gain of 3.2 times 10 to the negative 4. Okay. So you don't have to write all this in your ICE table if you can understand how the values go in there. Okay, so all we need to do is figure out, and then this is 3.2 times 10 to the negative 4. Okay, all we got to do now is figure out what the question mark is. And the way that we're going to determine that is we're going to use our Kb value, because we know that Kb is equal to the concentration of HClO and OH minus. So if you guys notice, we're kind of just doing the same thing over and over and over again. Okay, it's just different ways of doing it. And then we just need to plug in our values and we should be good. Okay. So I'm going to give you guys about, let's say 3 minutes. I want you guys to finish up the problem and I want you guys to find the question mark. If you want to finish up the rest of the problem, go ahead. Just make sure you're very careful with what you're trying to find. But I'll give you guys about 3 minutes to try to finish up the question and we'll go over it to make sure we have the right answer. Okay, so I'm not going to go through all the calculations because it should be pretty easy for you guys at this point. You can use the 5% rule here. Yeah, and so for your value for your question mark value should be about 0.31. Got that?
Yes.
Okay, so what this means is that we initially start with 0.31 molarity ClO minus, okay? Unfortunately, we can't just stop there because in the question, what unit of measurement is it asking for? Moles, yeah, it's asking for moles. Now, since we know that it's a 1-to-1 ratio between these, we can interchange this with NaClO, but we do need to plug it into the molarity equation in order to finish out the problem. So it's going to be 2 liters on the bottom, 0.31 molarity. We multiply by 2 on both sides, and you'll get a final answer of 0.62 moles of NaClO. So that's the original amount of NaClO that went into our solution. Okay. So yeah, I'm like multi-step problems now. Okay. Any questions? Easy? Hopefully. Maybe not. Hard for me too. I'm cheating right now.
You're cheating?
Yeah, I'm making the stuff up as I go. It's all fake. Okay, guys, let's move on. I'm not gonna do 12.41 with you guys because it's a pretty similar problem. If you guys want to try it out on your own, you can. So I will give you the answer. So if you want to write this down on your paper, you can. But the answer for 12.41 is going to be 0.123 molarity NH3. So if you want to try this as a practice problem, it's very similar to the one that we just did. And see if you want to see if you get the right answer, it's 0.123 molarity NH3. Okay. If you want to jot it down for future reference, you can. Just another practice problem for you guys to do, but I'm not going to be going over this in detail. Okay. Okay, so let's move on to the next part. We're going to be talking about in the next part the relationship between Ka and Kb. Okay. So we can derive this with a very long proof, but I didn't want to go over that proof because I ain't got no time for that. So if you want, it's on page 679. But what you can just copy down is that Kw is going to be equal to Ka times Kb, and that's equal to 1 times 10 to the negative 14. So if you guys notice, it's the same thing for the concentration of H plus and OH minus in water, right? Yeah.
But it's only
At 25 degrees Celsius. And typically you're going to be working in that range. Yeah.
they don't respond to.
Yeah. Mhm. But they should be telling you that it's 25 degrees Celsius. All right, now the important thing about this equation is it basically just tells you the again, you guys already know this. It tells you the relationship between the strength of an acid and base. So the stronger the acid, the weaker the strength of the conjugate base, and vice versa as well. It's just telling you that there's an inverse relationship between the two. Okay. And then down here, you can take a look at the table just kind of as a proof. We'll take a look at HF. HF is the acid. It's somewhat of a strong weak acid, but this is its Ka. And its conjugate base is super weak. It's a super weak base because HF is relatively a stronger weak acid. Okay. So it's just telling you that the conjugate base and the acid will have inverse relationship in terms of their Ka and Kb values. Okay. That's pretty much it. All right. Another type of measurement you want to be familiar with is pKa. Now this is very similar to pH, pOH. There's also pKa. There's also pKb. And at this point, you guys should be able to tell that the P basically means negative log of whatever measurement you're doing. And then same thing as before with pH and pOH. If you add pKa and pKb, it equals 14. Okay, so everything is kind of just interconnected with each other.
Who decided it was gonna be 25 degrees Celsius?
It's just an easy temperature for them to work with. I don't know. I told you this is all fake. I made this up.
This.
Did
you see the hail yesterday?
It was snow.
It's all fake.
How would they know?
Because it's not in the system that we're working in. So. The Bailey system, right? Yeah. I don't know if that answer would fly. They'll just think you're a crazy person. Yeah. Yeah, so you fit in perfectly. If anything, you might even exceed the expectation. The greatest chemist of all time. All right, you can try making that argument on the AP test. Yeah, I'll back you up.
You go now.
Alrighty, guys.
No,
So if you guys have all those equations, were you guys able to write this down?
Yeah.
You guys got this as well?
Yeah.
Okay, I want you guys based on that information to find the Kb of a fluoride ion. Okay. So very simple, fluoride ion is right here. You guys have the Kb. I just want you guys to Wait, did I write this wrong? Oh, I'm stupid. I apologize, guys. PKB, my fault. How did I not catch that last year? Alright, so I want you guys to calculate the PKB of a fluoride ion just to make sure that we're all good with our calculation. This should be really quick. I'll give you guys a minute to do that. How did that get past me last year? Easy. So what we're gonna do for this one is we're gonna use the PKB formula. We know that it's negative log, and then you got the KB right here. 1.5 times 10 to the negative 11, and you'll get a PKB of about 10.82. Okay, easy peasy. Now, if you wanted to get fancy with it, what you could do is you can actually use the Ka of the conjugate acid, negative log of 6.8 times 10 to the negative 4, and based on that answer, you can subtract it from 14 and get the same answer. So there's multiple ways you can do it, depending how fancy you want to get with it, but yeah. Or you can just do it, keep it simple. No, I believe this will be available for you on your screen. All right, let's move on. Okay, let's do this one. Okay, so I'm gonna give you guys about 3 minutes. You can try this with the person next to you. Here we have the base quinoline, and it has a structure just for you guys to look at. Conjugate base or conjugate acid has a pKa of 4.9. I want you guys to find the base dissociation constant. That's Kb. Okay.
I was there.
So you got your pKa, which is 4.9. You have the pKa formula, which is negative log of Ka. Now what we can do for our calculations, you want to move the negative to the other side first. And then in order to get rid of the log, you want to do 10 to the power. So 10 to the power cancels off the log. So Ka is going to be equal to 10 to the power of negative 4.9. Okay. And that's going to simplify to 1.259 times 10 to the negative 5. Okay. You guys good? Okay. Now we also know that Ka times Kb is equal to Kw, which is 1 times 10 to the negative 14. Right? So what we're going to do is, since we have Ka, we want to find Kb. We can isolate Kb by dividing by Ka on both sides. That's going to be 1 times 10 to the negative 14 divided by 1.259 times 10 to the negative 5. Okay, that's going to give us a final answer of 7.494 times 10 to the negative 10. Okay. I want to get fancy with it. If you guys found another way to do it and you can do it this way, you can do it that way. As long as the answer is correct.
Oh, no.
It's the way my twisted mind works. Make it harder for you guys. All right. Everybody good?
No.
Okay. What's wrong?
Oh, I'm just.
Okay, so we're gonna move on to the next section. I know this is a lot of text, but as I'm sure you guys are doing all your reading, right? For sure, yeah, okay. All right, so basically, when you have a salt, okay, and we're not talking about table salt, but we're talking about salt that's created when an acid and the base react with one another. So for example, you guys don't need to write this down, but a salt is basically the compound other than water that's produced when an acid and base react. So for example, we got HCl and acid, and NaOH, which is a base, right?
Yeah.
When they react, they're going to react to produce water, right? The H and the OH produce water. But the other chemical that's produced is NaCl, right? And so this other chemical right here is called the salt. Now, this right here is table salt. This is the thing that you put on your food. But if you guys want another example, we can just change up some of these. So for example, instead of that, let's say that we had F, and we had MgOH2, it would still create water. I'm not going to balance it, but it'll create MgF2, right? So if we do that, this is going to be the salt. The other ionic compound is going to be your salt. That makes sense? Yes.
The neutralization.
Yeah, neutralization.
Doesn't solve like how. Like the chart.
Yes, the charges need to neutralize out, yeah.
Mr. I have a question, not regarding this, but since you're back today, what are our titration going?
Let me check the schedule, depends how quickly we go. Yeah. I'll try my best to fit it in for you guys, though.
Okay,
Yeah,
thank
because I do want to do titration.
Like, how the calculations go?
Yeah, so if we aren't able to do it this unit, I promise you, we'll do all the labs we couldn't do without all the hard parts after the AP test, okay? Of course, you guys are the best. I appreciate that. I'm not though, but thank you. Okay, so that's what a salt is. Now, the thing about salts is that when you put a salt inside of a solution, I want you guys to write this down somewhere. Nearly all salts are strong electrolytes, so they dissociate completely. Okay, so salts aren't like weak acids where only some of them dissociate. Almost all salts, there's a couple exceptions, are strong electrolytes. So if I put MgF2 inside a solution, it will dissociate completely. Mg and F. Okay, so because of that, that's actually going to be changing up some of our calculations. If you have a salt inside of a solution, and if you have an acid and base in there too, the salt is actually going to affect the acid and base's ability to dissociate. And that's what we'll be talking about. But we'll get to that later. Okay. So let's take a look at a problem just to kind of put that all together. So let's go over 12.45. We're going to be looking at the effect that NO3 ions will have on the pH of a solution. Okay. Okay. So let's take a look at NO3. Okay, NO3 minus. So when we take a look at NO3 minus, okay, based on the terminology that we've learned so far, what type of compound this is? Okay, so it is polyatomic, but pertaining to this unit, it's a base. It is basic. Wow. Amazing. Okay, so it is a base. Now, specifically, it's a base relative to what?
The conjugate acid.
Yeah, the conjugate acid, or it's the conjugate base of a specific acid. What acid is it a base to? Yeah, HNO3. So HNO3 is the acid. Okay, and HNO3 in solution is going to dissociate into H plus and NO3 minus. Everyone can see that, right?
Yes.
Now, this is the acid, and this is let's say that this is the conjugate base, because what we really care about is the HNO3. What type of acid is HNO3? Yeah, it's strong, right? It is very strong. So complete ionization. Okay, so basically what we're looking at in this scenario is, let's say I have a container. Okay, another beautiful drawing. Color. Wow. I know, thank you. It's amazing. I am my drawings are very special, yes. Okay, so let's say that we have some NO3 ions inside of our solution, right? And then let's say that we add HNO3 in there. Okay. So just based on what you guys know about strong acids, if I add HNO3 into a solution that already has NO3, will it affect HNO3's dissociation?
Yes.
No. Okay, the reason why is because it's strong, right? Strong acids, by definition, they fully dissociate, right? Okay, it doesn't matter if there's other ones in there, if it has the other ions in there, because you're thinking probably chandelier principle, right?
Yeah.
You got this, it should affect this. But because it's a strong acid, that's why it's important to be able to recognize strong acids. Because it fully dissociates, NO3 minus will not have an effect on its ability to dissociate. Okay, so the answer to part one right here will be nothing. Okay, it will not affect the pH. Okay, and then your justification, if you want to write it, is because it is the conjugate base of a strong acid. Okay, so let me pull up something to write with. Okay, so you can write that NO3 minus ions will not affect pH because It is the conjugate base of a strong acid, which fully dissociates. Okay. So that's kind of the general gist. Does that make sense, guys? Yeah. Okay. So yeah, conjugate bases of strong acids don't affect the pH because the HNO3 is going to dissociate no matter what. Okay. That's why it's a strong acid. Okay, so with that being said, I'm going to give you guys about 3 minutes, and I want you guys to write the answer and justification for the effect that carbonate ions will have inside of a solution. Okay, so I want you to do the second part right here. What effect will CO3 2- carbonate ions have on the pH of the solution? And see if you guys can write justification for that. Okay, guys. So let's talk about it. Some of you guys might not have been as detailed as I wanted, but it's okay. Let's take a look at it. So first of all, will CO3 2- ions affect pH?
Yeah.
Yes. Okay, no Spanish. I don't speak Spanish, man.
My first language.
I failed Spanish. You're just pointing that out that I failed Spanish.
Josie doesn't speak Spanish.
Yes, I do.
Your first language probably is not Spanish.
Yes, it was.
Is it really?
Yeah. Speak.
Are you messing with me?
Spanish anymore?
See, now you're just doing it to just make fun of me now.
Well, yeah.
Josie.
You know what? I'm gonna fail your next test and be like chemistry. Okay.
Nothing. Yeah.
All right. Okay. So yes, CO3 2- will affect pH.
Yeah.
Did anybody specify whether it will increase or decrease?
I think
Oh. Okay. I saw Josie's hand first. Josie, do you think it will increase? It will increase pH. Okay. What's your justification?
Because CO3 2- is a strong base, and its conjugate acid is a weak acid, so it won't fully dissociate.
Okay. So that was partially correct.
Okay.
No, that's good though. So
Brennan, what do you like?
CO3 2-, it is the conjugate base of an acid. Okay. Now, if you take a look at its acid, or sorry, if you take a look at its conjugate, it's going to be CO3, HCO3-, right? Now, if we take a look at this right here, is this a strong or weak acid? Yeah, this one's weak. Okay, now, so if we take a look at this, it's going to be the conjugate base. Now, we can tell by its relationship that this is going to be relatively a stronger, it's going to be a strong weak base, okay? Because it's not one of the strong bases that you were told to memorize. Okay, so this is still technically not a strong base, so you don't want to identify it as a strong base, especially since it's not one of the ones you were supposed to memorize. But
How would you describe it on it?
you would say that it dissociates more than its
Okay.
conjugate, yeah. Or you can say that it is a stronger base than this is an acid,
Okay.
yeah. So yeah, so just, yeah, I know it's confusing because it's stronger weak base or weaker, yeah,
It's a
but
weak base, but it's on the stronger.
yeah, it's on the
Like-
stronger
like-
side of, yeah, on the spectrum of that. So, yeah, so just be careful with your terminology. And yes, so because it is the conjugate base of a weak acid, that's correct. CO3 2- carbonate, it will increase pH. Yes.
I said, well, I like to reference, why do you say CO3? So that, because I referenced, instead of saying HCO3-,
Yeah.
I said H2CO3. Would that count?
No, that wouldn't work because that's gonna be a different, remember polyprotic acids are stepwise, so it'll
Yeah.
release one. And then it'll release a second. This will be the second dissociation from H2CO3. Yeah, I mean, if you want to refer to it to say that makes this weaker, then you can do that, but you'll have to mention HCO3- being the conjugate acid.
No, I did.
Yeah,
I
then
said-
you're good.
I
Yeah.
mentioned how it's the second form of the conjugate base. It's in the second
Yeah.
step.
Yeah, that's
Okay.
works.
Italian. Separation, for example.
Okay, everybody good? You're good? Okay, and if you want to be a little bit more specific, you can say it'll increase pH because higher pH means more acidic or basic.
More acidic.
Oh, wait, let me think about this.
Thanks.
I mean, more basic. Yeah.
Remember,
More basic. Because,
Wanna-
because it's on the really low ones, it's like lemon.
Yeah. yeah, higher pH values mean more basic. Okay, more basic means Is there less or more H plus?
Less.
Less H plus, which checks out with our logic here, because if you got more of this guy, which way is it gonna push the reaction, left or right? So left. And you guys are saying all the options. Okay, so let's go through a step by step just so we're all good. Okay, carbonate will increase pH because a higher pH means more basic. If something is more basic, there is less H plus, right? Okay, and there is less H plus because a CO3 2- pushes the reaction left. So if you take a look at this, it's going to push it left. If it pushes it left, that means that it's going to decrease the amount of this, which means less H plus, more basic, higher pH. Yes.
So would carbonate react with water, then create HCO3 minus and OH, or does it only react with like one of the H's?
So it'll react with so you can either think of it as H plus or H3O plus.
Okay.
Yeah, because it's, I mean, that water's in equilibrium
Yeah.
too. Yeah.
Okay.
Good question. Yeah, so it'll basically react with whatever it can grab.
Sure, can I get water?
Yes, go ahead. Yes, we'll take a potty break right now.
What is like
All right, so we're back on the record with the recording, and Josie said that if when she thinks of a color for me, she thought of the color yellow. I don't know why she thought of yellow,
Because you're so,
but take it as you will. Why? You find it?
No, I just figured out how to.
What does it mean? Is it yellow? It's yellow? So, okay, hold up, Josie, before we move on the record, we are on the record. Why do you think of the color yellow when you think about me?
I wonder why. Oh. No, stop. There's like that some Ford commercial where it's like, I'm black, I'm white, I'm red, I'm yellow, and it's like, it's so stupid, but I always think of
But why do you think of yellow with me specifically?
I have no idea. I don't
Oh, my fault. It's okay. I probably think I think of the color.
So again.
There's nothing to get. Wait, that's so stupid because guys, I'm gonna be the first one to admit it. I am kind of yellow. My skin color is yellow. I reflect the color yellow mostly. Maybe a little red because of the blood too. Maybe a little white because I'm pale too, but whatever.
So they're gonna be red.
Red, white, yellow. Yeah, red, white, and yellow. Oh, so close to America. Should have been blue. Okay,
you have like blue veins.
I do have blue
Like a
veins.
pure-
Cancel culture is so stupid. Okay, anyway, let's move on. So, okay, so we figured out the effect that ions have on pH. Make sense? Okay, now it gets a little bit more complicated with other salts. So for example, salts that have ionizable protons. So for example, the one that we just looked at, HCO3 minus, that's one with an ionizable proton. There's also this one right here, HSO3 minus. These are amphiprotic, which means basically they can either become acid or base. So this guy, well, this guy's not going to go that way because it's H2SO4. But for example, this one right here, this one can go to H2CO3, but it can also go to CO3 2 minus, right? So it can act as either an acid or a base, depending on what reaction it is undergoing. So for these kinds of polyprotic ones, you're going to want to remember this rule. Okay, so if the Ka is greater than the Kb, the ion causes the solution to be acidic, and then the reverse as well. Kb is greater than Ka, the ion causes the solution to be basic. Yes.
For those who usually have a way that like one is stronger, like are they stronger as acid or base?
That's going to be determined by the Ka and the Kb
Oh,
value.
so they don't have like one's equal. This
Yeah.
one is
Mhm.
strong when it's an acid.
Yeah. Mhm. You're
Yes?
gonna want to take a look at the K and
Okay.
Kb value. That's how you determine. There's no general rule, like,
Okay.
yeah, to memorize. Or I guess this is a general rule, but good question. Yes, Robbie, can you stop? What is he doing?
Playing chess.
I'm not playing
He's
chess.
reviewing his chess game.
No, good for you. Are you good?
No.
It's okay.
We both beat him.
She
Yeah,
didn't
I
beat me.
beat
She
him.
didn't beat me.
I beat you.
Hey, there's
earlier.
nothing wrong with it. That's a hard game.
She made it so I didn't.
Okay, guys, ready to move on?
I know, why is everyone all of a sudden?
Okay, so, we just looked at anions. Now we're gonna look at cations. What's up? Yeah, it's been going on and off. All right, so we're gonna cations. Okay, so the first type of cation, we're gonna take a look at our polyatomic cations. The ones that you see the most, the one that you will see the most is NH4 plus. Okay, NH4 plus is a weak acid and donates a proton to water, which will lower the pH. Okay, so this is kind of a general one. You're gonna wanna, I guess, remember. You don't need to memorize it, but just kind of understand the concept why. Excuse me, NH. Oh my god. Sorry. You'll see NH3 a lot, which is a weak base, which means obviously NH4 plus is the conjugate and it's a weak acid. And so it's going to donate a proton to water. And if there's more protons, it'll lower the pH. Okay, easy way to remember it. This one you might want to keep or just memorize, I guess, because this is just very commonly used. Okay, there's no other real example they use other than this one. Yeah.
Okay, so the conjugate of a weak base doesn't always have to be a strong acid. It's only if it's a weak base.
Yeah,
Strong
so-
acid or strong base of the conjugate.
Yeah, so it's either stronger or weaker.
Okay,
Yeah, but
but if
doesn't
they're strong, their conjugate is
always weak.
But if
Exactly.
they're weak, they could be stronger. but they're
Stronger.
still weak.
Exactly. Yeah, very confusing. A lot of ers. Okay, next one is metals. Metals are the other cations that we can think about. I'm gonna scroll down a little. So, for example, what I mean by metals are things like this, right? Metals that have a specific charge. Metal ions, they react with water to decrease the pH of an aqueous solution. Okay, so just keep that in mind. That you'll have to memorize. If you got a metal ion, they're gonna react with the water and they're gonna decrease the pH. Okay. I got a little diagram right here for you. I'll go down to it in just a second, but just make sure you guys jot that down. And then the other thing that you want to keep in mind is that as the ionic charge increases, the acidity will also increase. Okay. And I'll talk about why in just a sec, but just keep that in mind. Metal ions, they're going to react in water to decrease the pH.
Thanks, Ralph.
Hey, I'll see you. Have a good one.
See ya.
Thanks.
Bye, Susie.
Okay, so first let's talk about why metal ions, they react in water to decrease the pH. Now, metals typically have what kind of charge? Positive or negative? Positive. So metals are positive. So if you put a metal inside of water, water we know is autoionizing between H plus and OH minus, right? So if you put a metal inside of water, which one of these is going to react with? Yeah, OH minus. So the metals are going to react with OH minus. And so if there's less OH minuses, what is there more of? H plus. And so if there's more H plus, that's going to decrease the pH. Okay, make sense? Also, the other thing to keep in mind is that the stronger the ionic charge, so let's say that we have something that's 2 plus. Now, if we take a look at mole ratios, this guy's going to be able to take up more hydroxides, right? Because it's going to want to bond with more of them, which is going to even further increase the H plus, which will even further decrease the pH. Okay, so this is something just to keep in mind. The stronger the positive energy on an ion, metal ion, the lower the pH is going to go because there's going to be even more H pluses available because it's going to eat up all the OH minuses. Okay, make sense? That's kind of the reasoning behind it. Yeah.
You think like eat up OH, just like.
It's gonna bond with. It's gonna bond with them. It's gonna bond with the free OHs inside a solution.
Make water?
No. So it's going to make the hydroxide. So for example, the Fe. So Fe2 plus is gonna react with the OH minus inside of water.
Yeah.
To produce FeOH2. So it's gonna produce a salt basically.
Okay.
Yeah. And then if it was, yeah, you get the point from there, right? Cool. Okay, let's keep going. And that's pretty much what this was talking about. All right, so we'll end with this. And this, I'm not gonna finish going over, but I want you guys to just kind of read this on your own. This page right here, if you guys want to jot it down in your notes, what page is this? Page 40. So on page 40, it's gonna tell you the effect that cations and anions have in solution, and that's what we'll kind of end off on today. I'm not gonna go over these. I want you guys to read this on your own. I know that everybody does their reading so diligently,
We do.
on time,
Yeah.
all the time. And so just one more thing to read. These are just some rules to keep in mind, okay? So this is how different cations, anions, and different quantities of them will affect the solution. And then we'll come back and do 12.46 together next time, okay?